Hello, everyone, and welcome to this Orolia webinar on the next generation of CRPA testing, reimagined for the user. We'll start with a few housekeeping issues. This webinar is being recorded for those who are unable to join us today. Feel free to submit questions throughout the meeting using this questions feature that's shown here. At the end of the meeting, we'll choose a few questions for the panel to address. So you feel free to type in questions as they come to you during the meeting. If for some reason you lose your connection, you can join again using the same meeting link. Our speakers for today are Tim Erbes, Director of Engineering at Orolia Defense Security, Stephane Hamel, Director of Test and Simulation for Orolia, and Lisa Perdue, Product Manager at Orolia. Our agenda today includes choosing the correct simulator, what is CRPA, what is Wavefront UHU demo. We'll have then a presentation on SkyDweller technology and then testing methods and benefits. At the end, we'll have our Q&A session where we'll share some of the questions that you submitted and invite the panel to respond to those. And we'll close by talking about the next webinar event on July 16th. At this time, I'd like to hand it over to Tim Erbes to talk about choosing the correct simulator.
Thank you. So when we talk about simulation and GNSS simulators, we need to make sure we choose the correct simulator for the platform that's under test. Now, most use cases start with the single vehicle use case. There are billions of devices on the planet that are single antenna GPS receiver. So this is the most common use case by far, and this is a good fit for our BroadSim or our GSG 6 or 8 simulator offering. These are simple patch antennas or normal antennas like you see in the picture there. And this is kind of the starting point for how you think about the types of simulation we're going to talk about. So the next level up would be a multi-vehicle simulator. This would be useful for RTK-based rover setups or drone swarms, as you see in the picture there, or examples where you have two vehicles that need to dock or drive together and then part. This is not a very common use case, but it is definitely supported. You do need to have multiple simulators in order to perform this. And because of the nature of the simulation, this would not be compatible for an anechoic chamber. And we're going to talk about that in a little bit. Another similar use case, not to be confused with multi-vehicle, would be a multi-antenna use case. So this is when you have more than one GPS antenna installed on the platform. In this case, we're looking at the top of a precision ag tractor setup, and there are two separate antennas. But again, these are just normal patch antennas. These devices are used for more accurate heading and roll, typically found on construction and agricultural equipment. Again, it's not a super common use case, but it is supported and it does require multiple simulators. And because the antennas are at two separate locations, these are not compatible with anechoic chambers. But the focus of today is the multi-element use case. Typically, we refer to these antennas as CRPA antennas. There are other reasons you might have a multi-element use case. Typically, we're talking about anti-jam or direction finding or angle of arrival. These systems are becoming more common. The amount of CRPAs on the market is increasing, and we sort of think that we're going to start seeing this stuff in more commercial applications going forward. So this is a more common use case that when you think about simulator selection. And we do offer BroadSim Wavefront and GSG Wavefront, which are simulators that can fully support this use case. And that's primarily what we want to talk about today, is how do we design a simulator to do that, and what are the capabilities? And again, these type of antennas are compatible with anechoic chambers, which we will talk about in a little bit. So what is a CRPA? You may hear this acronym a lot. What is it? So a CRPA is a special antenna. It's a controlled reception pattern antenna. And in this little picture, you see kind of an airplane with a multi-element, in this case, 7-element antenna on the top. And with these 7 elements and some complicated matrix math, the antenna's pattern can change dynamically in response to jamming or spoofing signals. And the idea is to null out the direction of where a jammer is coming from so that you do not receive that RF power into your GPS receiver. And by adapting the pattern, you can react to threats in real time. So this is like a very useful antenna system for platforms. And that is why someone would need to test in a wavefront environment, is to test these types of anti-jam antennas. There are other use cases for similar antennas, like angle of arrival or direction finding applications. They're very similar in nature, and a lot of the same things are true. So it's not just about AJ, but AJ is probably the most common example of a SERPA antenna. So what does one look like? So here's a few pictures of the components needed to have a SERPA system. So it starts with some sort of multi-element antenna. In this case, this is a 4-element antenna. There are 4 separate RF spigots coming off of the bottom of this antenna that would then be directly connected to the antenna electronics unit. Now, the antenna electronics really is the part that we refer to as the SERPA. There's nothing really special happening in the antenna itself. It really just is 4 separate antennas in a single enclosure. The real magic is happening in the antenna electronics. And then the RF comes out of the antenna electronics and proceeds to the GPS receiver. So a lot of times you'll see SERPAs or antenna electronics sold as a solution where you can install them in existing platforms to protect the existing receivers. So the antenna electronics is the part we're really talking about today, but you actually kind of need all 3 pieces to have a full SERPA system. And we're going to talk about how that impacts how you go about testing a system like this. There are other styles of SERPAs available, single enclosure or sometimes called integrated SERPAs, where the multi-element antenna and the antenna electronics are in a single enclosure. Fundamentally, they work the same way, but it's not as obvious that there are multiple cables involved. And the bottom of this antenna only has 1 RF spigot. So it's fundamentally the same, but you have to think about differences when it comes to testing because of how it's physically constructed. So the simplest way to test a SERPA antenna or the whole system is to place it in an anechoic chamber. So in this example, we have the GSG anechoic or the Broadcom anechoic system provides the RF signals into the transmitters inside the chamber. And those signals are radiated to the multi-element antenna and the antenna electronics and the GPS receiver. And this is a very simple use case to understand because you're basically just taking the whole system as it would be installed and placing it in the chamber and testing it that way. There's really nothing kind of special happening here. The fact that you're using real spatially separated signals and they're presented to the antenna preserves the nature of those simulations so that the SERPA receives the signals it should see. You do test the antenna. It is part of the test in this case. And we're going to talk about when you use simulation, you don't actually have the antenna. We're going to compare those. And in either case here, whether it's an integrated or a separate system, all the components just get placed in the chamber. When you're testing with a simulator that's not radiating, like an anechoic chamber, so in this case, a direct inject, or sometimes we call it a conducted test, where you physically connect the RF cables to the device under test. The antenna is not a part of that test. So I've crossed off the multi-element antenna, and I'm just showing that we have the antenna electronics and the GPS receiver under test. Now again, the magic of a SERPA is in the antenna electronics. So this is still a very good test to test the SERPA's reaction to the threats and the environment around it. But it's important to note that the antenna itself is not part of this test. So what do you do in the case of an integrated or a single enclosure SERPA? How do you use a simulator to test it? Some people think you can't, but you can. Typically, it requires some cooperation with the manufacturer, but basically what has to happen is you have to take the top off of it and you have to get access to the RF connectors inside and connect directly that way. And so we have removed the multi-element antenna in this case, and we are connected directly to the antenna electronics. And once you've physically made these connections, the test can proceed as normal. So you've heard me use the term wavefront. I've thrown that around a little bit, but what is a wavefront? Well, let's think about what happens when a signal from outer space arrives at an antenna location. So we have a faraway source, so it shows up as just a flat wave to us, and it comes across and hits our antenna. Now, depending on the angle of the arrival of this wave, that RF wave is going to hit the different elements at different times. So in this case, I'm showing a 4-element antenna, and I've color-coded each element. And from the point of view of the wave, we can see that the first element that's hit is the orange, then the red, and then the green, and then the blue. And the timing of the wave hitting these elements is very critical to have a valid simulation. Any small error in the simulation would break down the signal environment in such a way that it is no longer a valid test. So if I have multiple signals, whether it's satellites from outer space or jammers or spoofers, this is just happening many times. We have many signals arriving, hitting the antenna elements, and from the point of view of the wave, and now I have color-coded the waves, you can pick one of the RF waves, like take the orange wave, for example, and you see it hits the elements in a precise order at a precise time. One good example here is the green wave hits the orange and the green element at almost the exact same time, and then slightly later, the blue and the red element at almost the exact same time. And this kind of illustrates why it's so critical to get the alignment just right, because if the alignment's off, you actually hit the wrong element first. And this can cause problems in the math that the SERPA is going to perform. Now, from the point of view of the antenna elements, the picture looks just a little bit different. So if you look at the bottom left, I have, from the point of view of the element, so for example, the orange element's on the top, it gets hit by the orange wave, and then a little bit later, the blue and the green almost at the same time, and then the red. And so again, from the point of view of the element, the timing and the arrival of RF signals is absolutely critical. Any error in the alignment, and you've now destroyed the simulation. So I'm gonna let this play a couple more times, but I've actually just added a picture of a software-defined radio next to the antenna elements on that animation to kind of picture this idea that as long as you stream the right signals into the radios at the right times, the RF signals being generated by those radios will in fact be the correct signals for the simulated environment. And as long as those radios are phase aligned, you have preserved the necessary timing restrictions on the simulation. So for example, if I look at the red element, as long as the blue wave gets sent to the radio followed by the orange, and then some time passes, and then the red, and then the green, as long as we preserve that timing alignment, we've created a valid simulation. I'm gonna let it play just one more time, and then we'll move on to bringing the whole simulation together. So how do we go about creating the simulation and streaming this? So we start off in the modeling and simulation world. We have the vehicle trajectory, we have the antenna pattern, we have the satellites, we have the jammers and the spoofers. There's all this information is being modeled and contained in this modeling and simulation world. We then determine what digital IQ data must be generated to create the simulation, and that digital IQ generation actually happens inside of these high performance GPUs. And the digital data from the GPU then has to be streamed to the software-defined radios, specifically phase-aligned software-defined radios. And each radio corresponds to a specific antenna element in the simulated world. And then each radio generates an RF signal that gets passed to the antenna electronics. And as long as the phase alignment of that RF signal is preserved, the signals that end up presented to the antenna electronics are correct according to the model and the simulation, are phase aligned, and so the SERPA can perform the necessary math and have a valid, accurate simulation. So this is the concept of how a Wavefront simulator works, and we're going to show you in a little bit how we've gone about making these things happen, and how do we go about keeping those phase-aligned radios, in fact, phase-aligned. So we have, I'm going to show a little video of a demonstration, but before I show it, I want to make sure you understand the setup. So we have a Wavefront simulator. In this case, we have a 4-element Wavefront simulator, and we've directly connected the 4 RF cables to a very interesting device. So this is called the North Star. It's a product by Yoo-Hoo Technologies. It's kind of like a SERPA, but it's a little bit different. It has 4-element input, but instead of doing like AJ stuff, instead what it's doing is angle of arrival by looking at like interferometry in the CA code. And this is a very kind of unique application that is only just fairly recently available. But the reason we're talking about it today is it has this great way of showing visually what is happening in the simulated environment. And so I'm going to show you what the simulator looks like and what the device under test looks like. And I'm kind of testing both at once. I'm using the simulator to test the North Star, and I'm using the North Star to test the simulator. This is kind of a tricky problem. How do you have confidence that your phase alignment is correct? Now, we have our own ways of testing phase alignment, but we wanted a way to show the full system operating and working correctly. And so that's what we've done here. Now, we do have a full-length video available. We're going to send a follow-up email after the webinar is completed. And in that follow-up email, you'll have a link to the full-length video. The one I'm going to show you now is a little bit shorter, but it has the really important visualization. So in this simulation, we have on the left is what you see on the simulator, and on the right, we have the web UI of the device under test, the North Star. And on the right-hand side, you see a sky map of the locations of all the satellites. The blue dots represent the locations based on the broadcast data from the satellites. So this is where the satellites should be. And the green dots represent the location that the satellite appears to be coming from based on the angle of arrival as determined by the 4-element array on the North Star. Now, I'm going to kind of back up the video so we can see that beginning part again, because it didn't last very long. But when it starts off, the green dots and the blue dots are in the same location. Now, you see there's a little bit of variance on some of them. That's normal and typical. We see the exact same thing when we connect to a live sky antenna. We're talking about a really low power signal here, and so it can be tricky to get the exact angle. But you see some of them are spot on, so it's doing a pretty good job. Now, at the very beginning of this test, the spoofer is transmitting signals, and the North Star shows that there's some power coming from the southeast. So the power was detected first, and that was shown as like a jammer. But then shortly after those signals were turned on in the simulation, all of the green dots moved to that southeast on the horizon. So what's happening is the angle of arrival of all of these signals is no longer coming from outer space where they should be. They're actually coming from the spoofer location. And so this is important for a few reasons. One, it shows that the Yoo-Hoo North Star is correctly determining the angle of arrival of these various signals. So that has some big implications for the users of this product. But also, it's showing that the simulator is able to simulate multiple signals, in this case, true signals and spoof signals. And in fact, the spoof signals do have the correct characteristics in the simulation to appear to have come from the correct location based on the simulated model that I've generated. Now, in this case, I just have a simple spoofer flying a circle around my location. And as that circle is flown, I should see the location of the spoof signals move over time. And so I'm showing that on the right-hand side. So again, both products are being used to test each other. It's sort of a chicken and the egg problem. But you can see that as the spoofer moves, the apparent angle of arrival of all the spoof signals also move. And then at this point, I'm fast forwarding the video a little bit, just so you can see that, it continues to form this circle, and you can continue to see these green dots all the way coming from the spoof location. A couple of times you'll see like there's GPS 10 came from the true satellite. And you actually, I want to point out a couple of these satellites like GPS 23 is being tracked from the spoofer, but the blue dot indicates that satellite 23 is actually below the horizon. It's not even visible. And that's because the spoofer is transmitting a signal that's not in the true sky, and that's a valid spoofing test. And the North Star indicates that it's tracking the signal that should not be visible. Okay. So I'm going to hand over to Stephane Hamel. So he's going to talk about some of the technology that we've built to make this wavefront simulation possible.
Thank you, Tim. All right. So I will begin by giving some clarification on what is SkyDweller and what do we mean when we say we have a software-defined architecture. It's important to understand those terms correctly so that you can follow the rest of the presentation. So first of all, SkyDweller is a software. It's a real-time simulation software and it runs on Linux or Windows. And to generate GNSS signals, it requires a GPU that we use as a co-processor. And it requires a software-defined radio to convert the IQ baseband signal into RF. So we selected high-end CUTS hardware to create turnkey systems like the BroadSim and the GSG8, but it's possible to run SkyDweller on your own hardware. So because SkyDweller can run on off-the-shelf hardware like GPUs and radios, that's why we can say it's a software-defined architecture. It runs on not on any hardware, but it's not so dependent on the hardware. So this architecture allows us to scale down to meet simpler requirements, or we can scale up to test SRPA electronics. So in this webinar, we'll focus on how we scale up to run SkyDweller to support anechoic and wavefront systems. So this is two examples. On the left, you see the anechoic chamber, and on the right, the wavefront simulation. So on the left, the simulator is actually connected to antennas in the anechoic chamber, and we have multiple antennas transmitting the signals. So it's not one antenna per vehicle. It can be multiple vehicles transmitting through the same antenna if they come from the same region in the sky. So the closer they are in the sky, the more likely they will be transmitted from the same antenna. So all the signals from all the satellites are being transmitted in the anechoic chamber, and we have a special calibration tool that will calibrate the system for a very specific point inside the chamber. So that's why Tim earlier said that multi-antenna, if they're far apart, might not be suitable in the anechoic chamber, but for a SRPA antenna, it's perfectly suitable because it's very close, the elements. So we calibrate the anechoic chamber and the anechoic simulation system to have the correct time of arrival and the correct power for a specific spot in the chamber where you will place your device under test, your SRPA antenna and the electronics. On the right, it's a bit different. It's the wavefront simulation. We will bring cables to the antenna electronics. So we call that conducted test, where we have to bring all the signals for each element using cables. So here we show the solution for wavefront simulation for the conducted test. We'll talk a bit later about the anechoic chamber. So here what we show is the system architecture. We always use in every wavefront system that we build, we use the same architecture, but we can scale up and down depending on the number of elements, and the number of signals will maybe dictate the number of GPUs we need, number of computers, and so on. But the principles is always the same. The architecture starts with having simulator nodes. So each node will simulate all the signals that goes to a specific element of the SRPA electronics. So if you have a 7-element SRPA electronics, we can use 7 nodes to generate all these signals. Each node will simulate the low power signals for the truth signal, the GNSS, and we also have the high power signal for jammers, spoofers, or other type of signals that can be much stronger. So we have 2 different RF paths, so we can manage this huge dynamic range in power, but then these signals are sent to the RF distribution module at the bottom, and then we will mix and combine the signals and bring the proper signals, low and high power, to a specific element. This RF distribution module will also provide a feedback loop to the simulator controller. So the simulator controller is it's like the heart of the system. It will control all the nodes. It will coordinate them, synchronize them, and send them work to do to simulate the proper phase alignment and dynamics and so on. And it's monitoring the combined signals that feedbacks the controller so that we can measure the phase in real time. So we can make compensation and corrections during the simulation to make sure that the phase stays within the specification of the system. And because we do this not only at the beginning of the simulation, but continuously during the entire duration of the simulation, we can be sure that we stays within specifications regardless of the duration of the simulation. The simulator controller not only controls the nodes and the feedback loop, it's also the single point of interface for the user. So from the user perspective, it still behaves and it's still being used as a normal simulator for, like the BroadSim or the GSG8. It's the same user interface. All the complexity of having multiple elements that needs to be phase synchronized, time synchronized, and so on, all of that is happening under the hood, and it's transparent for the user. So the user can only concentrate on what needs to be achieved in terms of test. So defining the scenario, the jammers, the spoofer, where they are located. If you have multiple jammers, multiple spoofers, and so on, you can create your scenario and not worry too much about how the system works behind, because everything is automated, including the calibration. And the way we're doing it, we use special algorithms that will look at the phase difference between each pair of elements. And we have a very fast algorithm that can do that in just a matter of a few seconds. So in less than a minute, you will have your entire system calibrated, and it will start. And then it will, about every 10 seconds, do a spot check on the phase to make any necessary correction if needed during the simulation. So you spend time creating your scenario and testing your device instead of waiting for your system to calibrate or waiting for your system to do work that you shouldn't be waiting for. So you spend more time focusing on your test. A very important characteristic of a good simulator is to make sure that you can simulate not only the GNSS signals, but all the threats, the jamming, the spoofing, the repeating. And it's especially important for SERPA because SERPA are designed to be resilient in very harsh conditions. And the first thing you need to ask yourself is, will my tool help me to test the limits of the system? So if you have a 7-element or 16-element SERPA electronics to test, you know that you have to simulate many jammers and many spoofer before you can reach the limit of what the SERPA can take. So you have to make sure that your simulator can take all these threat simulation workload easily and in an easy way to do. So right from the start, it was built in the simulator that you can simply decide, okay, I'm going to put a transmitter here, and that transmitter will transmit a custom waveform. It can be an IQ file, it can be different basic modulation, and you can combine multiple waveforms to create very complex waveforms. And then you will move your transmitter around, and then you can see from different directions how your SERPA electronics will behave. And then you can add a second, a third, and then 10, 20, 50 jammers if you want. So when you want to simulate a spoofer, there's a lot of attributes that are similar to a jammer. So you have to define where it's going to be transmitting from, where it's going, if it's moving or fixed, what's the power, what's the transmitting antenna pattern, because it could be doing a beam in one direction and so on. So because we did all of that for the jamming simulation, for the spoofing, we simply add a different type of waveform to transmit. So instead of transmitting basic waveform, it can transmit the GNSS signal simulated by another instance of the SkyDweller simulation engine. So now you can have multiple SkyDweller engine connected together that will transmit the truth signal and the spoofers. And the spoofers will be mounted on these virtual transmitters So the simulator will take care of all the dynamics and the added range for the transmission and the effect on the phase, the Doppler, and all that is taken care of. So it's really a matter of few clicks to put a transmitter in space, associate another SkyDweller instance as the spoofer trajectory, and start the simulation. So that's really having the built-in jammer and spoofer in SkyDweller really makes it easy to create very complex scenarios that were not even possible just a couple of years ago. So all of that is now built in. And we talk about software-defined architecture. So what does it really mean for the user? Well, it means we're not attached to a specific hardware design, and the design never gets old because we can always upgrade the PC with better GPU, better CPU. So every time Intel or NVIDIA invest massive amount of R&D to improve their hardware, we can leverage that R&D and integrate those new solutions into our system and have more channels. So when a customer asks us, how many channels or how many signals can you simulate? Well, my answer is always, how many do you need? Because we can simply scale up the system. So as you can see on the right here in this computer, we have 8 GPUs and 2 CPUs. So SkyDweller can leverage all of this processing power, and in this single computer here, we can simulate over 1,000 signals. And if you look at the picture on the left, this is a Wavefront simulator that the Orolia Defense and Security built. You can see that there are 7 boxes with red LEDs on the front. So each of these boxes is the computer on the right, and it's one node. Like I explained a bit before, each node will simulate all the signals for one element. So this is a Wavefront simulator for a 7-element SRPA electronics testing. And so why do you need 1,000 signals? Well, like I said earlier, when you test a SRPA, the whole point of testing a SRPA is to reach the limit of what the SRPA electronics can do. And if your electronics pretend to be able to know 6 or 7 jammers or 6 spoofers or 6 repeaters, you have to be able to simulate all these signals in real time. So when you simulate repeaters and spoofer, it's very, very GPU or processing. It requires a lot of processing power because it's actually simulating all the same things that you would do for the truth signal. So you need all these processing power to simulate multiple repeaters and spoofers. So that's what this architecture allows. We can scale up with these powerful computers. So just to recap on the key features of the Wavefront simulation that we have a system that can scale up and down from 2 elements only up to 16 elements. Not that we cannot do more than 16 elements, but so far we haven't seen a system with more than that. We can cover 4 frequencies for low power and high power. And these low and high power are combined for each element. We have a continuous phase synchronization, so we can in real time calibrate the phase, the time, the power, and we have very tight specifications here to be able to test the SRPA electronics. And it's very start. The algorithms that we develop allows you to create a scenario, and when you click start, the system will auto-calibrate in few seconds and then continuously during the entire duration of the simulation. And very importantly, the interference, jamming, spoofing, and repeating, everything is built in. It's not an afterthought, so it's well integrated and easy to use in the GUI or in the API. So you can automate everything with Python, C++, C#, or whatever your favorite language. You can automate everything in your simulator. So now we'll jump on the Anechoic solution that we have. So again, to test SRPA electronics, but instead of doing it with conducted signals, we use an anechoic chamber and we transmit over the air. So what we show on the screenshot here is that some signals from different locations in space will be associated together and transmitted via the same antenna. So this way, with a limited number of transmit antennas, 16 or 32, you can cover the entire sky, and we can have unlimited number of satellites. If they're close together, they will be transmitted through the same transmit antenna. And we also simulate all the jammers. So an antenna transmitter can be programmed to transmit either GNSS signals or high-power jammers and spoofers. So for the Anechoic system, one very interesting feature that we developed is the ability to auto-calibrate again. So what you do is you simply place an antenna where you want to have your device under test located. So you place an antenna here in that specific location, you click a calibration button, and we will calibrate all the time delays, the power, and all of that will be automatically calibrated with the signal that we send. And then you can run your scenario and everything will be properly calibrated and submitted for that specific location. So that completes my section of the presentation. So now we'll ask Lisa to take the mic from here.
Hey, thank you, Stephane. So Tim and Stephane gave us a great detailed look at testing multi-element antennas using a simulation system. So now we're going to take a look at how that compares with other testing methods. So different methods for testing include record and replay, GNSS simulation, anechoic chamber, and field test. So starting with record replay, this is a solution that could work, but there's really no commercial solution available today that covers testing of SERPA using record replay. So it would have to be a custom developed solution. The fidelity you can see is good. It's realistic because it's actually recorded data, not simulated or generated, but you're unable to change that recording. So once you have the recording, you can't make any changes to it. You're stuck with that test case is done with that recording. That's it. And of course, you still need to find a suitable environment to record. So you want to record threats. You have to go where threats are in order to record them. That can be really difficult. The GNSS simulator method is next. That's what we've been mainly talking about today. And you'll note that it's the lowest cost option on our list. So we've only been able to say that it's the lowest cost option for the past couple of years due to advances in technology. Previously, the old way of simulation testing required very complex phase matrix equipment, which was also very expensive. So if you ever considered a Wavefront simulator in the past, but you found it too expensive or too complicated, it's definitely worth another look because the technology has allowed us to do neat and innovative things with the Wavefront simulator. Simulation also gives us the flexibility needed to cover multiple test cases quickly, allowing for a fast iteration speed. Then the next is the anechoic chamber. So we're talking about a complete anechoic chamber system, including simulation equipment for it and actually standing up and implementing a full actual chamber, the physical chamber. So that one is very high cost and it's very high in effort as well, because you have to consider all of these different variables such as the physical limitations, building standards for wherever it is that you're trying to put the chamber. And there's also can be a lot of unknowns and things that you'll run into during the installation that's all going to add up into more effort and more cost. And then we take it to the field test. So this is a way where you can go out in the field where they're going to simulate threats in an artificial environment and you're able to test your devices. But this is another area where the costs add up. So the event needs to be staffed, licenses for each threat must be obtained per whatever the local regulations are. And as an attendee, you have no control over what those threats are that are being generated. And that gives you limited access to the threats, and you won't be able to cover all of your test cases. So it's really a high-level comparison of the different methods and the key points on each. But in reality, it's probably best to combine some of these methods. So for complete testing, you could start with a simulation system for fast iterations, then rent space in a chamber or attend a field test event for complete system testing. So combinations of these are definitely encouraged and is the way to go to test the complete system. So taking a deeper look into anechoic and wavefront options. So now we're really focusing on the simulation systems as Stephane presented them in the last section. So we have some pros and cons for each. The anechoic system allows testing of both the antenna and the antenna electronics. It's the only way to test the integrated device. So if they put the antenna and the antenna electronics into a single package, without modifying it, this is really the only way to test it would be using radiated, as Tim explained earlier. But it does require that there's a chamber available that's sized for the device under test. You could be limited by the antenna setup in the chamber. So that really can impact, the chamber itself, and the physical chamber can impact how the simulation, how accurate and how good, realistic the simulation can be in an anechoic chamber. For the wavefront, we're looking at, the ability to have dynamic trajectories for the receiver and for the interference transmitter. So that allows us to do a lot of testing. We can really model whatever type of scenario that we want to. We can test unlimited number of interferences. It's also lab ready. It doesn't require a complex installation. Like an anechoic will take a lot of time to do the installation, get the test set up right, install the antennas appropriately. We don't have that with the Wavefront system. You can get it, it's already set up, ready to use. The only con with the Wavefront system, as we mentioned several times earlier, is it doesn't include the actual antenna in the test. But the important part to test is the antenna electronics, as Tim mentioned, so it's still a very good solution for testing SERPA. Looking specifically at the SkyDweller benefits for anechoic and Wavefront, we can see that for anechoic, there is the automatic chamber setup and antenna mapping that Stephane mentioned earlier, and that's all done via the software. For Wavefront, we can have a large number of interferers, and the system is provided in a noise-reducing rack, so it can keep your lab quieter. And then we have the benefits of both systems share, such as the compact form factor, the automatic calibration. Again, it only takes a few seconds before the simulation in order to calibrate the system. We have the higher performance that we've discussed, and the built-in directional jammer spoofers and repeaters. So that's very important. It's all integrated in the system. All the complex calculations are already done for you behind the scenes. It's very easy to use. But then we add to that all the benefits of the SkyDweller simulation engine itself. So this is just what you get with the SkyDweller simulation engine, not directly related to anechoic or Wavefront. That's the powerful API and automation, the user interface, the reliability. So we'll be able to run our longer tests with confidence, and I'll talk about that in just a minute in the next section. So for this section, I really just tried to put together something that can try to explain the number of small details that we need to be aware of that can have a big impact on the overall Wavefront solution that you choose. So when you're selecting a Wavefront system, there are a lot of questions that you should ask. So I set this up as a section as a series of questions that could be asked of any Wavefront simulation provider. And of course, I'll give you the answers for the Orolia Wavefront systems. But again, you can, these type of questions should be considerations that you think about whenever you're choosing a Wavefront simulator as well. So the first one is phase alignment. So as we've discussed, this is so important in Wavefront. It's not sufficient to only synchronize the simulators with 10 megahertz and PPS. We have to have phase stable or a set of phase matched cables with the system, and the phase has to be calibrated. That's a must. So the questions that you can ask are, how often should the phase alignment be calibrated or checked when running the simulation? So as mentioned earlier, we are going to do continuous calibration with real-time feedback, so no additional checks or calibration is necessary. You'll be able to see at any moment of the simulation what the phase alignment is. How long does it take prior to running a scenario to calibrate the system? So with the Orolia Wavefront, we've mentioned it's less than a minute. I put in minutes here, to be a little bit conservative if you're doing all frequencies and all signals, but it's really still less than a minute. And we ensure that the accuracy is maintained throughout the simulation. And then is there a time limit on how long you can run a scenario for and maintain the phase calibration? So the Wavefront systems from Orolia can run for an unlimited amount of time, and you can have the confidence and the accuracy with the phase alignment for the duration. So you can leave it for the weekend and come back, and you shouldn't have any doubts whether it's going to be work and stay aligned. And then you can even look back to verify that that was true. So this is the example of the real-time monitor and correction of the phase. So here we can see this is a 4-element system. Element 1 is not shown because it's the reference that we're comparing each other element to. So from this chart, you can see the relative accuracy between all of each element, so all of them versus element 1, and then you can also compare them to each other. So it gives you this, this is a screenshot of the simulator. So it gives you this information in real time for as many elements that are supported in your system, and you can see that it's, you can see what it looks like over time and then what it is at right now. Then we get into jamming and spoofing simulations. So Stephane spent quite a lot of time on this. So it's really the same information with the same answers, but it's just framed in a question sort of way. So the anti-jam antenna systems, so SERPAs, antenna electronics, we usually say that they can create, this is just one example, n-1 nulls, where n is the number of elements in the system. So it would be like a 7-element system can create 6 nulls. So given that example, we want to make sure that any of our simulation systems that are used to test these anti-jam antenna systems need to be able to simulate enough jammers and spoofers to reach the limitation. So in this case, we want to be able to generate more than 6. If this is what we're testing, is for the number of nulls, and test that each one, can work and provide a good solution. So that's an important factor to consider as well. So how do you configure the jammers and spoofers in the Wavefront system? That's a question we can ask. And our answer from Orolia is that we take advantage of the advanced jamming and spoofing capabilities of the SkyDweller software-defined simulator. That's what Stephane was talking about earlier, is that how it's out. So it's integrated, it's built in, it's not an afterthought or a piece that was added to the system. It was designed to work with the GNSS system from the start. So it allows us to the easy configuration for the jamming and spoofing systems. It's just, right in the same GUI. How many jammers can I have on the Wavefront system? How many spoofers? So we can have hundreds of jammers on the Wavefront system if desired. The number of spoofers is really only limited by the system license. And if we know how many spoofers you want up front, we'll make sure you have the right processing power to provide signals for that number of spoofers. As Stephane showed earlier, we can just add more processing power wherever we need it to generate the additional signals. And what is the jammer to signal ratio achievable with the Wavefront system? So the Orolia Wavefront systems can achieve 120 dB J to S. So the jammer to signal ratio, you'll see it somewhere earlier we had just said greater than 110. And here I'm just saying 120. So it's not a direct specification that way, but in any case, we can do greater than 110. But we need that high J to S. We need to be able to test the device under test to its limits. That's important when we're testing anything. We want to be able to push it to its limits and see what happens. And then the final area is system scalability and upgrades. So as threats evolve, anti-jam antenna systems will evolve, they'll add new capabilities, increase number of elements, they'll support additional GNSS frequency bands and signals. So we know that Wavefront system is a large investment. We want to make sure that it's going to be usable for us in the future as well. So we can ask the questions like, what if I want to add additional signals to the Wavefront simulation? Do I need to purchase additional channels? So as Stephane explained earlier, we're not limited to any number of hardware channels. We can always generate all-in-view signals for any constellation. So adding any additional signal support is typically just a software upgrade. In some cases, you may need additional processing power in the form of a GPU. If you're adding new frequency bands, new signals that need additional RF, we can add an SDR to the system, but we're not adding a whole new box usually or a whole new simulator. It's more like just adding the components and pieces needed to scale it up, and the system doesn't really have a limit on how high it can be scaled up. We can just keep doing that to meet any system needs. What if I want to add more spoofers? So adding spoofers to us is the same as adding additional signals to the system. So it'd be the same answer as the first one. It's not separate hardware, it's just need to make sure that we have enough processing power to generate all the signals needed for the GNSS and the spoofers. And if you already have that, it's just a software license. Otherwise, we can add components. And then as the system grows, do I make any performance compromises at any point? So let's say I have a system today, I want to double the size of that system. Am I going to make any compromises in the performance? And for us, the answer is no. The specifications are going to remain the same regardless of how large the system grows. Then to wrap that up with some key takeaways, is that purchasing a Wavefront system is complex. It is a large investment. So even though I mentioned it was the lowest cost option of everything, when you consider all the different variables, it still is expensive. I mean, that's just the reality of it. So we want to make sure that we understand everything we can about it before the purchase. So we want to be aware of any limitations in the system, and if there's any limitations when we add additional functions, signals, jammers, spoofers, whatever it is that we want to add, grow the system into. Ensure the system is scalable for the future needs. So inquire now, ask now. Can I upgrade it to, from a 4 to a 7 in the future, from a 7 to a 16 in the future? And what's that going to cost me, approximately? And then remember, take a look at what's out there today. And it's not just Orolia, but there's other vendors to take a look at. Talk to us, and we can say goodbye to those expensive, rigid, and limited solutions. We can really, with today's Wavefront systems, they're really more capable than ever. They're easy to use. You don't have to be some type of GNSS, RF engineer in order to use them. We can actually simulate threats that are difficult to reproduce even in field testing. So it's a nice repeatable way to do your testing for your SERPA system. So for more info, you can go to our websites. So we have Orolia.com, and we have Orolia Defense and Security, which is AuroliaDS.com. And you can go there and look for the products, GNSS simulation or BroadSim Wavefront on Orolia DS, or you can just contact us. Email address is fairly simple here, sales@Orolia.com. Send an email there and we will answer your questions for you. And with that, I'll turn it back over to Jennifer to take us into the Q&A section.
Thanks, Lisa. So we have some good questions today, and we're going to start out with this one. Is the equipment flexible to upgrade? If we have a 4-channel SERPA setup, can it be upgraded to a 5-channel easily later?
Yeah, so the main component of the system is actually the software, and you can purchase a system with the number of elements you need today, and then later you could increase to the different number of elements. If you happen to know in advance that you plan to or might want to upgrade in that direction in the future, we'd want to discuss that up front just so we can make sure we leave enough room in the physical spacing of the equipment and how we set it up. But you can certainly start with a 4-element and then later move up to a higher element count.
Okay, and our next question is, what maximum interference power can you get out of the Wavefront simulator?
I can take this one. So the way it works, we have dedicated RF outputs for jamming and for GNSS, so it allows us to have a very wide dynamic range because the power for the jammers are using more amplification, so we can have a maximum output power for the jamming at -10 dBm. So it gave us a J2S of about 120 dB, and the GNSS signals who are on different RF band, they will work at a lower power. So that's how it's designed.
Thanks. Okay, so our next question is, can the system simulated GPS, CA, P code, and M code as well?
Yeah, so for GPS, CA code, and P code, the answer is definitely yes. If you need Y code and M code, the answer is also yes, but you need to work with Orolia Defense and Security, and we will work with you and the GPS director to go through the security process to get Y code and M code, and those are fully supported.
Okay, and our next question is, does the Wavefront simulator have a way to account for the antenna element radiation pattern?
Yeah, so like we explained, it's basically the same engine that works for non-Wavefront and Wavefront. So for Wavefront, we actually combine multiple antenna patterns works normally in the SkyDweller engine. And what you do is you define the physical location of these elements, and each element can have a different antenna pattern where you can orientate the antenna in the way you want. You can have different gain, phase offset based on the elevation and azimuth of that specific element and how the signals reach the antenna. And so it allows you to actually reproduce the pattern of an existing SERPA, or you can create your own experimental pattern and see how these electronics will behave with different patterns. So you have the full flexibility on having different patterns for each element, how you locate them, and how you orientate them.
Thank you. And the next question is, will the system maintain automatic phase calibration even during a long duration, high power jamming simulation?
Yeah, I can take this one too. So yes, it does, no problem. Like I said, the GNSS signals and the jamming are using a separate RF path, so that any jamming signal, regardless of the power that you transmit, will not impact our ability to monitor and calibrate the phase on the GNSS signals. And because the RF outputs for the high power and low power are paired, they're always phase aligned by design. So we just need to make sure that we monitor the phase on the GNSS signal, and the jamming signal will follow as well.
Okay, thanks very much to our panel for going through these questions and answers. Hermes, we have a record of the questions that were submitted. And now, since we're moving toward the end of our event today, I just want to point forward to the next event, our Orolia P&T Coffee Talk webinar. The next one is on July 16th at 2 p.m. Eastern, where we will be talking about P&T vulnerability testing for critical infrastructure, lessons learned from defense. Registration is now open on our website, orolia.com, under resources, and we hope to have you join us there. Thanks to everyone for joining, and the on-demand video will be available soon.